Hey Marcus, welcome back to Physics Lab Podcast. Today we're diving into something that happens all around us, but most people never think about: thermal expansion. Have you ever noticed how a metal bridge has those special gaps in it?
Actually, I have. I always wondered why they don't just build the bridge as one solid piece. Is that related to thermal expansion?
Exactly. Those gaps exist because metal expands when it gets hot and contracts when it cools. If there were no gaps, the bridge could crack or buckle. But here's the really interesting part. This happens at the atomic level, and it's all about how atoms behave when they gain energy.
Okay, so let's start with the basics. What exactly is happening at the atomic level when something gets heated?
Great question. Imagine atoms in a solid material as tiny spheres connected by invisible springs. At room temperature, these atoms are vibrating, but they stay relatively close together in a fixed pattern. When you add heat to the material, you're essentially adding energy to the system.
So the atoms vibrate more.
Precisely. When temperature increases, the atoms vibrate with greater amplitude. Think of it like shaking a spring more vigorously. The atoms move farther from their equilibrium positions. Because of the way atomic forces work, atoms can move farther away from each other than they can move closer together.
That's an interesting asymmetry. Why is that?
It comes down to the shape of the potential energy curve between atoms. At very close distances, there's a strong repulsive force. At larger distances, there's an attractive force. The repulsive force is steeper than the attractive force, so when atoms vibrate more, they spend more time at greater separations. This causes the average distance between atoms to increase.
So the whole material gets bigger because the average spacing between atoms increases. That makes sense, but I have another question. Why do different materials expand by different amounts?
Excellent observation. This is where the coefficient of linear expansion comes in. Different materials have different expansion coefficients, represented by the Greek letter alpha, or alpha. The change in length is given by the equation delta L equals alpha times L naught delta T, where L naught is the original length and delta T is the temperature change.
So alpha is like a fingerprint for each material.
That's a perfect way to think about it. Different materials have different atomic structures and different bonding strengths. For example, copper, aluminum, and brass, which we actually test in our lab, all have different expansion coefficients. Aluminum expands more than copper for the same temperature change.
Why would aluminum expand more than copper?
It's about the strength of the atomic bonds and the mass of the atoms. Aluminum atoms are lighter and have weaker metallic bonds compared to copper. This means the atoms can move farther apart more easily when heated. Additionally, the shape of the potential energy curve differs between materials, affecting how much the average atomic separation changes with temperature.
That's really cool. So in our lab experiment, we're measuring this expansion by heating tubes and using a dial gauge to measure how much they expand, right?
Exactly. We use a steam generator to heat the tubes to a high temperature, and we measure the change in length with a precision dial gauge. Each increment on the dial represents 0.01 millimeters. We also use a thermistor to measure the temperature change accurately.
And then we can calculate the coefficient of expansion for each material.
Yes, by rearranging our equation, we get alpha equals delta L divided by L naught times delta T. So if we measure the original length, the change in length, and the temperature change, we can determine alpha for each material. It's important to note that alpha can vary slightly with temperature, but within the range of our experiment, we treat it as constant.
This is really practical stuff. Understanding thermal expansion is crucial for engineering, isn't it?
Absolutely. Engineers must account for thermal expansion in everything from bridges and buildings to airplane fuselages and railroad tracks. If they don't, structures can fail catastrophically. That's why bridges have expansion joints, and why power lines sag more in summer than in winter.
One more thing, you mentioned that some materials are isotropic. What does that mean?
Good catch. Isotropic materials expand uniformly in all directions. Copper, aluminum, and brass are all isotropic metals, so their expansion coefficient is the same whether you measure along the length, width, or height. However, some crystalline materials are anisotropic, meaning they expand differently depending on the direction. For those materials, you'd need to measure expansion along multiple axes.
This has been really enlightening, Priya. So to summarize, thermal expansion happens because atoms vibrate more when heated. The average distance between atoms increases, and different materials expand at different rates based on their atomic structure and bonding characteristics.
You've got it. And by conducting our lab experiment, we're not just observing this phenomenon, we're quantifying it and understanding why materials behave the way they do. That's the power of experimental physics. Thanks for joining us on Physics Lab Podcast.